Hello everyone, my name is Almir and I'm the captain of Team BRATVA. Today I would like to present our final project, which is devoted to the numerical simulation of a double pendulum using differential equation and Python. First, let me introduce the members of our teams. There are Sultan Muhit, Asanghali Bigzat, Ilesov Shokan, Birjanov Amir and Mirjan Murat. The objective of the project was to derive the equations of motion of a double pendulum, solve them numerically, and create a computer simulation. To achieve this, we followed several steps. First, we derive the equations of motion. The second, we implemented the mathematical model in Python, and we analyzed the behavior of system using numerical simulation. So, a double pendulum is a mechanical system consisting of two rigid rods connected by hinges. Also, the system appears to be simple. Its motion is highly nonlinear and may become chaotic. This makes the double pendulum one of the classical examples of nonlinear dynamics. To simplify the mathematical model, we assume that both rods are muscles and that the masses are concentrated at the ends of the rods. The first step is to describe the geometry of the system. Using the kinematic constraints, we determine the Cartesian coordinates of both masses. After that, we differentiate the coordinates with respect to time to obtain the velocity components of each mass. Knowing the velocities, we calculate the kinetic energy of the system. Next, we determine the potential energy produced by gravity. Using these expressions, we construct the Lagrangian, where L equal to T minus V, where T is the kinetic energy and V is the potential energy. So let's find the kinetic energy. The velocities are equal to the sum of the derivative of x and y. So let's find the T1 and T2. By identity of trigonometric formulas, we will simplify the equation of T1 and T2. Now let's find the potential energy. The projections of the two triangles in this case will be equal. Minus L1 cosine theta 1 and minus L1 cosine theta 1 plus L2 cosine theta 2. And after that, the Lagrangian will look like this. Let's substitute all of our values into the Euler Lagrange equation. For theta 1, the system will look like this. Now let's derive the complete equation. Note that if we add the damping coefficient, we get the following equation. Look, if we take into account the damping coefficient, the equation will take the following form, where C1 is damping coefficient. The damping coefficient or damping factor is the ability of a system to control and damp unwanted oscillations, and dimensionless quantity that shows the ratio of the actual damping of oscillations to the critical one. Let's do the same for theta 2. Let's write out the system. Let's find the complete equations. Let's substitute C2 for theta 2, where C2 is the damping coefficient for the second hinge. After deriving the equations, we implemented them in Python. The system of differential equation was solved numerically using the solve IVP function from the CP library. The animation was created using matplotlib. First, we ran the simulation without damping. As expected, the total mechanical energy remains constant, which confirms the law of conservation of energy. Next, we introduce relative large damping coefficients. As you can see, the oscillations decay very quickly, and the second rod no longer has enough energy to perform a complete rotation. Finally, we reduce the damping coefficients by a factor of 100. Now the pendulum continues to exhibit chaotic motion, while its energy decreases gradually. Now let's modify the initial value of the second angle θ2. Also, the change is relatively small. The resulting motion becomes significantly different. This demonstrated one of the most important properties of nonlinear systems: sensitivity of initial conditions. Even a small change in the initial conditions may produce completely different trajectories. Next, we change the gravitational acceleration from Earth's value of 9.81 meter per second square to Moon's gravity, which approximately 1.62 meter per second square. As expected, the pendulum moves much more slowly because the restoring force is weaker. The fast portraits clearly illustrate the nonlinear nature of the system. Unlike a simple pendulum, the trajectories do not form simple closed curves. Instead, they exhibit complex structures that are characteristic of chaotic motions. The kinetic and potential energies are continuously exchanged. Because damping is included in the model, the total mechanical energy gradually decreases over time. In conclusion, we successfully derived the equations of motion of a double pendulum using the Lagrange method. We implemented the mathematical model in Python, solved the system numerically, created a computer simulation, and analyzed the influence of damping, gravity, and the initial conditions of the motion of the system.